Thus, we see that on the basis of energy bands, materials can be classified as conductors, semiconductors, and insulators. With conductors having a very small or nearly zero band gap, semiconductors having a finite and small band gap of less than 3 electron volt, and insulators having a band gap of greater than 3 electron volt. A semiconductor, without any artificially added impurity, is called an intrinsic semiconductor. Both silicon and germanium, the two most commonly used semiconductors, exist as intrinsic semiconductors. Let us take a look at the atomic structure of silicon and germanium. Both silicon and germanium have 4 valence electrons. In crystalline form, each silicon and germanium atom uses its valence electrons to form 4 covalent bonds with 4 surrounding atoms. Let us use the crystal structure of silicon to further study intrinsic semiconductors. Remember, the following discussion applies equally to germanium in its intrinsic form. At absolute zero, all the covalent bonds in the crystal lattice of an intrinsic semiconductor are intact. Thus, at absolute zero, there are no free electrons to occupy the conduction band, and the intrinsic semiconductor behaves like an insulator. However, at higher temperatures, some electrons gain enough thermal energy to break free of the covalent bonds in the crystal lattice. These free electrons move to the conduction band, and the material starts behaving like a semiconductor. Note that each electron that moves to the conduction band leaves behind a vacancy in the valence band. This can be visualized as breaking of a covalent bond, where an electron becomes free and leaves behind a vacancy in the covalent bond. An electron breaking away from a covalent bond takes away a unit negative charge with it, leaving behind a vacancy with an assumed unit positive charge. A vacancy with a unit positive charge in a covalent bond between atoms of a semiconductor is called a hole. Thus, whenever a covalent bond is broken in an intrinsic semiconductor, a free electron and a hole is created. We refer to this as an electron-hole pair. Hence, in an intrinsic semiconductor, the number of free electrons is always equal to the number of holes at any given moment. Consider a hole or a vacancy at position 1 in the crystal lattice of a semiconductor. Now, an electron from position 2 can jump to occupy the vacancy at position 1. This fills the vacancy at position 1 but creates a vacancy or a hole at position 2. Similarly, an electron from position 3 can jump to occupy the vacancy at position 2. This fills the vacancy at position 2 but creates a vacancy or a hole at position 3. As a result of such jumps of electrons across covalent bonds, the holes or vacancies appear to move across the crystal lattice of a semiconductor. Note that the movement of holes occurs because of the movement of electrons across covalent bonds in a semiconductor, and not because of the movement of free electrons. Thus, there are two types of moving charge carriers in the crystal lattice of a semiconductor: the negatively charged free electrons and the positively charged holes. When an electric field is applied across a semiconductor by connecting it across the terminals of a battery, the free electrons move towards the end connected to the positive terminal and generate an electron current denoted by IE. The holes shift towards the end connected to the negative terminal and generate a hole current denoted by IH. The total current flowing through the semiconductor is equal to the sum of the electron current and the hole current. If a free electron collides with a hole, it fills the vacancy in the covalent bond without the generation of any other hole. This is called the process of recombination. Under thermal equilibrium, the rate of generation of free electrons and holes in a semiconductor is equal to the rate of their recombination, so that the density of charge carriers in a semiconductor remains constant. As we learnt earlier, a pure semiconductor without any impurities in it is called an intrinsic semiconductor. Both silicon and germanium exist as intrinsic semiconductors. There are two types of charge carriers in the crystal lattice of an intrinsic semiconductor: the negatively charged free electrons and the positively charged holes. The conductivity of an intrinsic semiconductor increases with rise in temperature, as more number of electrons break away from the covalent bonds of the semiconductor atoms. However, at room temperature, intrinsic semiconductors have very low electrical conductivity. The electrical conductivity of an intrinsic semiconductor can be improved by increasing the number of free electrons or holes in it at room temperature. When a small amount of suitable impurity, say a few parts per million, is added to an intrinsic semiconductor, its conductivity increases to a large extent. A semiconductor that has an added impurity to increase its electrical conductivity is called an extrinsic semiconductor. The process of adding the suitable impurity to a semiconductor is called doping. Thus, an extrinsic semiconductor is also called a doped semiconductor. The impurity atom added to a semiconductor to increase its electrical conductivity is called a dopant. During the process of doping, the dopant gets positioned in the crystal lattice of the semiconductor. It is important that a dopant does not distort the crystal lattice of a semiconductor. For this, the dopant atoms of the semiconductor crystal should be comparable to the semiconductor atoms in size. We have learned that both silicon and germanium are tetravalent. That is, each of their atoms has 4 valence electrons. Commonly used dopants are either trivalent or pentavalent neighbors of silicon and germanium in the periodic table. Commonly used trivalent dopants that have 3 valence electrons are boron, aluminium, and indium. Commonly used pentavalent dopants that have 5 valence electrons are phosphorus, arsenic, and antimony. The addition of trivalent and pentavalent dopants creates 2 different types of extrinsic semiconductors. We know that in crystalline form, Each silicon and germanium atom forms 4 covalent bonds with 4 surrounding atoms. When a trivalent dopant, say an aluminium atom, is added to a silicon semiconductor crystal, the aluminium atom occupies the same position of a silicon atom in the crystal. A trivalent dopant atom forms covalent bonds with 3 neighboring semiconductor atoms. However, the dopant atom has no electron to share with the 4th neighboring semiconductor atom. Thus, a vacancy or hole is created in the lattice. Each trivalent dopant atom creates 1 hole in the crystal lattice of the semiconductor. At room temperature, some of the electrons break away from their bonds, giving rise to electron-hole pairs. Simultaneously, some of the free electrons recombine with the holes and reduce the number Ni of intrinsically generated electrons to Ne. Thus, the number of holes in a semiconductor doped with a trivalent dopant is much larger than the number of free electrons in it. We learnt earlier that a positive charge is assumed to be associated with holes. Thus, positively charged holes act as majority charge carriers in a semiconductor doped with a trivalent dopant. Thus, such extrinsic semiconductors are called p-type semiconductors. In spite of having the number of holes Nh greater than the number of free electrons Ne, the p-type semiconductor crystal remains neutral, as the charge of the additional charge carriers is equal and opposite to that of the ionized cores in the lattice. The movement of holes as charge carriers occurs when valence electrons from neighboring semiconductor atoms jump to fill the holes created by dopant atoms in p-type semiconductors. When a valence electron fills the hole generated by a dopant atom, the dopant atom becomes negatively charged. Thus, a dopant atom in a p-type semiconductor is called a negatively charged core or an acceptor impurity. A p-type semiconductor has an acceptor impurity energy band that lies just above the valence band. Thus, the free electrons can leave the valence band by covering a much smaller energy gap as compared to an intrinsic semiconductor. Valence electrons in p-type semiconductor can move from the valence band to the acceptor impurity energy band even at room temperature to create holes in the lattice. Thus, electrical conductivity of a p-type semiconductor is much better than an intrinsic semiconductor. Now let us see what happens when a pentavalent dopant, say a phosphorus atom, is added to an intrinsic silicon semiconductor crystal lattice. A pentavalent dopant atom in the crystal lattice of the semiconductor forms covalent bonds with 4 neighboring atoms of the semiconductor. The pentavalent dopant atom still has one very loosely bound valence electron that can be set free using a very small amount of energy. Thus, each pentavalent dopant atom contributes a free electron to the crystal lattice of the semiconductor. Therefore, the number of free electrons that are available for conduction by dopant atoms depend largely on the level of doping. If the doping level is high, the number of free electrons contributed for conduction by the dopant increases. This number of free electrons contributed by the donor dopants is not dependent on the temperature of the semiconductor crystal. On the other hand, if the temperature of the crystal is raised, the number of intrinsic electron-hole pairs increase, and this further adds to the conductivity of the crystal. Hence, in a semiconductor doped with pentavalent dopants, the total number of conduction electrons, Ne, is due to the free electrons contributed by the donor atoms, which are pentavalent dopants, and those generated intrinsically. But the total number of holes, NH, is only due to the holes from the intrinsic source. Due to the increase in the number of free electrons, the rate of recombination of holes increases. This gives rise to a reduction in the number of holes effectively as compared to the number of free electrons available for conduction. Thus, the number of free electrons in a semiconductor doped with a pentavalent dopant is much larger than the number of intrinsic holes. Negatively charged free electrons act as majority charge carriers in a semiconductor doped with a pentavalent dopant. Thus, such extrinsic semiconductors are called N-type semiconductors. When a dopant atom in an N-type semiconductor gives up a valence electron, it becomes positively charged. Thus, a dopant atom in an N-type semiconductor is called a positively charged core or donor impurity. A N-type semiconductor has a donor impurity energy band that lies just below the conduction band. Thus, electrons can jump to the conduction band by covering a smaller energy gap as compared to an intrinsic semiconductor. Free electrons released by donor impurity atoms in an N-type semiconductor can move from the donor impurity energy band to conduction band even at room temperature. For example, the energy required for an electron to jump from valence band to conduction band in an intrinsic silicon semiconductor is about 1.1 electron volt. If it is doped with a pentavalent impurity to a suitable level and converted to an N-type semiconductor, the energy required for an electron to jump from the valence band to conduction band reduces to 0.05 electron volt approximately. Similarly, if the semiconductor crystal is made of germanium, the energy required for an electron to jump from valence band to conduction band is about 0.72 electron volt. If it is doped with a pentavalent impurity to a suitable level and converted to an N-type semiconductor, the energy required for an electron to jump from the valence band to conduction band reduces to 0.01 electron volt approximately. Thus, electrical conductivity of an N-type semiconductor is much better than an intrinsic semiconductor. It can be shown that at thermal equilibrium, Ne into NH is equal to Ni square. Here, Ne, NH and Ni denote the concentration of electrons, holes, and intrinsic carriers respectively. You will learn about the details of the equation at higher classes. Let us recollect that extrinsic semiconductors are of two types: p-type semiconductors, in which the doping agents are the trivalent impurities, and in which the majority charge carriers are holes; and n-type semiconductors, in which the doping agents are the pentavalent impurities, and in which the majority charge carriers are electrons. Consider a p-type semiconductor crystal. to which a specific amount of a pentavalent impurity is added in high concentration. This creates a semiconductor crystal that contains both a p region and an n region. The boundary that separates the p region in the semiconductor from the n region is called the p-n junction. It is important to note that a p-n junction cannot be formed by joining two separate pieces of p-type and n-type semiconductors. Because of the surface irregularities of the two different crystals and because such continuous contact at an atomic level is not possible. If such a junction is formed, the junction would not be continuous and would therefore inhibit the flow of the charge carriers. Now, let us again look at the semiconductor crystal that contains both the p and n regions separated by the p-n junction. We know that in the p region, there is a higher concentration of holes, and in the n region, there is only a smaller concentration of holes. Similarly, in the n region, there is a higher concentration of electrons, and in the p region, there is a smaller concentration of electrons. This causes the holes to diffuse from the p region to the n region across the p-n junction. Physically, this means that some of the valence electrons just to the right of the junction may fill the vacancies just to the left to the junction. Simultaneously, the conduction electrons also diffuses from the n region to the p region across the p-n junction. The ions do not move because of their heavy masses. This diffusion of the majority charge carriers across the p-n junction creates a diffusion current that is directed from the p region towards the n region of the semiconductor. When electrons diffuse from the n region to the p region, they leave behind stationary, positively charged atoms of the donor impurity. Similarly, when holes diffuse from the p region to the n region, they leave behind stationary, negatively charged atoms of the acceptor impurity. This creates a layer of negatively charged ions towards the p side of the p-n junction, and a layer of positively charged ions towards the n side of the p-n junction. The layer of stationary negative charges towards the p side of the junction opposes the diffusion of electrons from the n side. Similarly, the layer of stationary positive charges towards the n side of the junction opposes the diffusion of holes from the p side. This creates an electric field near the junction, which is directed from the n side to the p side. Thus, a small region is created on either side of the p-n junction where no free charge carriers can exist. The region free of moving charge carriers extends on either side of a p-n junction and is called the depletion region. The separation of charges in the depletion region creates a potential difference that opposes the diffusion of electrons in the n region and holes in the p region across the p-n junction. The electrons and holes have to overcome this potential difference, called the barrier potential, to freely diffuse across the p-n junction. The potential difference across the depletion region gives rise to an electric field directed from the layer of positive charges towards the layer of negative charges. The electric field across the depletion region causes electrons in the p region to move to the n region. This is called the electron drift. Simultaneously, the electric field across the depletion region causes the holes in the n region to move to the p region. This is called the hole drift. This drift of minority charge carriers across the p-n junction creates a drift current that is directed from the n region towards the p region of the semiconductor. Thus, we observed that the diffusion current and the drift current across a p-n junction are opposite in direction. We have to remember that at the time of formation of the p-n junction, there is no depletion region. Thus, there is a high diffusion current but no drift current. As the depletion region gets formed, the diffusion current decreases and the drift current increases. In steady state, the diffusion current and drift current become equal in magnitude and there is no transfer of charge at any cross-section. Thus, a crystal with p-n junction in an isolated state is electrically neutral. A p-n junction with metallic contacts provided at its ends forms a basic semiconductor device called a diode. A diode is represented by the symbol shown here. Semiconductor diodes are the fundamental components of most of the electronic gadgets we use in our daily lives. We have learned that in a diode with metallic contacts, there is a p-n junction, separating the p side from the n side, and a depletion region which is devoid of any charge carriers. The holes are the majority charge carriers in the p side, and the electrons are the majority charge carriers in the n side. We have also learned that when the diode is not connected to the battery, the n side is at a higher potential and the p side is at a lower potential, and the diffusion current and drift current across the p-n junction are opposite in direction and equal to each other at equilibrium. It is important to note that the diffusion current is due to the movement of majority carriers of the p and n regions from one side to the other. Similarly, the drift current is due to the minority charge carriers of the p and n regions from one side to the other side. In this situation, the separation of charges in the depletion region creates a barrier potential that opposes the diffusion current across the p-n junction. We know that the barrier potential prevents any further movement of charges across the junction. Now, let the p-n junction diode be connected to a battery such that the p side is connected to the positive terminal and the n side is connected to the negative terminal of the battery. When connected in this way, the diode is said to be forward biased. When a p-n junction diode is in forward bias, the potential of the p side is raised and now the p side is at a higher potential and the n side is at a lower potential. Due to the forward bias connection, the barrier potential across the p-n junction decreases and becomes equal to the difference between the barrier potential V0 at equilibrium and the external applied voltage V. Also, when a diode is forward biased, the width of the depletion region around the p-n junction decreases. The lowering of the barrier potential and the decrease in the width of the depletion region leads to an increase in the diffusion of electrons from the n side to the p side. Simultaneously, the diffusion of holes from the p side to the n side across the p-n junction also increases. Since holes and electrons are the minority charge carriers in the n region and p region respectively, this increased diffusion of charge carriers in a forward biased diode is also called minority carrier injection. As a result of the minority carrier injection in a forward biased diode, the diffusion current increases much above its equilibrium value. But the drift current remains almost unaffected since the rate of formation of whole electron pairs is almost constant and is independent of the electric field applied by the battery. Thus, the diffusion current exceeds the drift current, and a net current flows from the P side to the N side in a forward-biased diode. The net diode forward current is equal to the sum of the whole diffusion current and the conventional current due to electron diffusion. This current is in the milliampere range. The net current flowing through a forward-biased diode can be measured using the circuit shown here. The diode D is forward-biased using the battery B. The diode forward current can be measured using the milliammeter MA. The potential difference across the junction is measured using a voltmeter V. The voltage across the junction can be varied using the rheostat RH. The graph showing the variation of current versus potential difference for a forward-biased diode is called its VI characteristics. The origin is the position of equilibrium when no external voltage is applied across a diode and no net current flows through it. The net current in a forward-biased diode remains zero or negligible until the external applied voltage reaches a certain threshold value. Beyond the threshold value, the net current in a forward-biased diode increases rapidly for small increases in the externally applied voltage. If the current increases beyond the rated value, it can get damaged unless it is protected. The current I in the circuit changes non-linearly with the applied potential difference, and hence the diode is said to be non-ohmic in nature. Now let us study about the reverse bias connection of a PN junction diode. For this, connect a PN junction diode to a battery such that the P side is connected to the negative terminal and the N side is connected to the positive terminal of the battery. Here, the P side of the diode is at a lower potential and the N side of the diode is at a higher potential since the battery raises its potential more than its value for the unbiased state. When a diode is reverse biased, the barrier potential across its PN junction increases and is given by the sum of the barrier potential V0 at equilibrium and the externally applied voltage V. Also, when a diode is reverse biased, the width of the depletion region around the PN junction increases. The increase in barrier potential width of the depletion region leads to a decrease in the diffusion of holes from the P side to the N side and the electrons from the N side to the P side across the junction. Thus, in a reverse biased diode, the diffusion current decreases much below its equilibrium value, while the drift current remains unaffected. The drift current is now greater than the diffusion current. Hence, a net current flows from the N side to the P side in a reverse biased diode. The net current is small, as the drift current itself is small, and hence the net current is even smaller. The net current flowing through a reverse biased diode is of the order of a few microamperes and can be measured using the circuit shown here. In the circuit diagram, the current in the circuit is measured using the microammeter. The potential difference across the junction is measured using a voltmeter V, and the applied potential difference to the diode can be varied using a rheostat RH. The diode is connected to the terminals of the battery such that its P side is now connected to the negative terminal of the battery, and the N side of the diode is connected to the positive terminal of the battery. The graph showing the variation of current versus potential difference for a reverse biased diode is called its VI characteristics for reverse bias. Under reverse bias, the net current, called the reverse saturation current, does not vary much, with increasing applied voltage, and is almost constant for small reverse bias voltages, until the applied voltage to the diode becomes equal to a certain voltage, VBR, known as breakdown voltage or cut-in voltage. When the applied diode voltage becomes equal to the threshold voltage or the cut-in voltage, the current in the circuit increases suddenly to very large values, causing a lot of heat to be produced in the diode, and hence the diode can get damaged unless we adopt some precautionary measures. Typically, the threshold voltage is nearly 0.2 volt for a germanium diode and 0.7 volt for a silicon diode. The VI characteristics of a diode in forward bias and reverse bias are shown on the same graph for a comparison between them. We observe that a diode allows a large amount of current to flow when forward biased. In reverse bias, diode allows a very small amount of current to flow, unless it is operated in the breakdown region. Thus, a diode is a device that allows free flow of electric current, or we say conducts, in only one direction when it is in forward bias. It allows little or no current to flow, or we say does not conduct, in the opposite direction when it is in reverse bias. We can also say that a forward biased diode offers low resistance, while a reverse biased diode offers high resistance to the flow of electric current. A diode is said to offer dynamic resistance that changes with applied voltage. The dynamic resistance R of a diode is given by a small change in applied voltage delta V divided by a corresponding small change in current delta I. Various components of electronic circuits communicate and work together through signals that consist of variations of current or voltage. A signal can be made of continuous variations of current or voltage, as in an analog signal. Or, a signal can be made of discrete values of current or voltage, as in a digital signal. A digital signal can only have a low and a high value of current or voltage represented by the numbers 0 and 1 respectively. Thus, digital signals consist of strings of zeros and ones called binary numbers. The circuits that control the flow of digital signals on the basis of a logical relationship between the input and output signals are called logic gates. The 5 commonly used logic gates are the AND, OR, NOT, NAND, and the NOR gates. Let us use simple circuits of one or more switches and a bulb to understand logic gates. Here, the state of the switch is the input that determines the state of the bulb that represents the output. An open switch represents an input of 0. The bulb remains off in this condition and represents an output of 0. A closed switch represents an input of 1. The bulb lights up in this condition and represents an output of 1. Now here is a circuit representing an AND gate. An AND gate has 2 or more inputs. The two switches A and B represent 2 inputs and the bulb O represents the output of the logic gate. Let us list all the possible input and output combinations of an AND gate in a table. When both the switches A and B are open, no current flows from them, so both the inputs are 0. The bulb in this case remains off, hence the output is also 0. When switch A is closed and switch B is open, input A is 1 while input B is 0. The bulb in this case still remains off, hence the output is still 0. When switch A is open and switch B is closed, input A is 0 while input B is 1. The bulb in this case again remains off, hence the output is again 0. When both the switches A and B are closed, both the inputs A and B are 1. The bulb in this case turns on, indicating this time that output is 1. An AND gate is represented by the symbol shown here. The table that lists all the logical input and output combinations of a logic gate is called the truth table of the logic gate. Thus, the table shown here is the truth table of the AND gate. The output of an AND gate is 1 only when inputs A and B are both 1. Now let us learn about the OR gate. Here is a circuit representing an OR gate. Just like an AND gate, an OR gate also has 2 or more inputs. Let us form the truth table of the OR gate. When both the switches A and B are open, no current flows from them, so both the inputs are 0. The bulb in this case remains off. Hence, the output is also 0. When switch A is closed and switch B is open, input A is 1 while input B is 0. The bulb in this case turns on. Hence, the output is 1. When switch A is open and switch B is closed, input A is 0 while input B is 1. The bulb in this case again turns on. Hence, the output is again 1. When both switches A and B are closed, both the inputs A and B are 1. The bulb in this case yet again turns on. Hence, the output is again 1. The symbol and the truth table of an OR gate are shown here. The output of the OR gate is 1 when either input A or input B or both are 1. Now, here is a circuit representing a NOT gate. Unlike the AND and OR gates, a NOT gate has only one input represented by switch A. Let us form the truth table of the NOT gate. When switch A is open, no current flows from it, so the input is 0. However, the bulb is turned on, hence the output is 1. When switch A is closed, assuming 0 resistance in the switch, all current flows through the switch and no current flows through the bulb. Thus, input is 1 and output is 0. The symbol and the truth table of a NOT gate are shown here. From the truth table, we can see that a NOT gate inverts the input. Thus, it is also called an inverter gate. An AND gate followed by a NOT gate forms a NAND gate. The symbol of a NAND gate is a combination of symbols of the AND and NOT gates as shown here. Note that in a NAND gate, the output of the AND gate acts as the input for the NOT gate. The output of the AND gate is inverted by the NOT gate and appears as the output of the NAND gate. Hence, if inputs A and B are both 1, the output of NAND gate is not 1. An OR gate followed by a NOT gate forms a NOR gate. The symbol for a NOR gate is a combination of symbols of the OR and NOT gates as shown here. In a NOR gate, the output of the OR gate acts as the input for the NOT gate and thus gets inverted. Thus, the input values in the truth table of a NOR gate are taken from the input values from the OR gate table. The output of the OR gate is inverted by the NOT gate and appears as the output of the NOR gate. NAND and NOR gates are also called universal gates, as they can be used to create all other forms of logic gates like the AND, OR, and NOT gates. Logic gates in a circuit are realized by combinations of electronic devices like diodes and transistors in combinations with resistors, inductors, and capacitors. For example, here is a circuit showing the construction of a NOT gate. Conventional circuits using a large number of electronic devices assembled together are bulky, unreliable, and prone to malfunction. Such circuits that use individual components are called discrete circuits. In 1958, Jack Kilke of Texas Instruments in USA created an integrated chip or IC that allowed circuits of a large number of electronic devices to be created on a single small chip of a semiconductor. The invention of ICs revolutionized the development of digital electronics, allowing increasingly complex circuits to be built onto increasingly smaller single semiconductor chips. Depending on the nature of the signal it can process, an IC can be an analog IC or a digital IC. A digital IC contains the logic gates we discussed before. Depending on the number of circuit components built on it, an IC can be classified as a small-scale integration IC, medium-scale integration IC, large-scale integration IC, or a very large-scale integration IC.